Welcome to physics exam questions on the topic energy changes in a system and the way energy is stored before and after such changes. That is 4.1.1 from the specification. This is a real past paper and it is the specimen paper. And it's triple higher. However, even if you're doing foundation or combined, you can watch this because all the questions in this video are also for foundation and combined students, and it's from the AQA specification.
This is the first question we're going to be looking at. It is from the specimen paper. Before I go to this question, I suggest that you pause the video and give this question a go by yourself. Now, to understand this question, you really need to understand the concept of resolution.
There are actually two definitions of resolutions. The first is the one mostly used in biology and is related to microscopes. It's just a measure of detail. So if there were two microscopes and one was to have a higher resolution than the other, then the one with the higher resolution would produce a more clear image where you can see more details than the microscope with a lower resolution. But obviously, since we're doing physics, this one is more relevant to our question. It's the smallest change in quantity that a measuring instrument can detect or display. So it's specific to a measuring instrument, a thermometer in specific, the one we were looking at the question. So we can see the temperatures on this thermometer. So if we have 17, what's the next temperature that can be detected after 17? It's 18, and after 18 is 19. So as you can see, the smallest change is 1. So the resolution of this thermometer would be 1. Since we understand resolution, let us get back to the question. For the temperature of the water to increase by 0.6 degrees Celsius, so we have to find which of these options is most appropriate to 0.6 degrees Celsius and can capture that specific number. Now, if you look at 0.1, it goes up. The resolution goes up in 0.1. So we know that 0.6 will come up eventually because after 0.1, it's going to be 0.2, then 0.3, 4, 0.5, 0.6. So this is actually the correct answer because 0.6 is going to come in a thermometer with this resolution. However, the second one, 0.5, the next one is going to be 1, so it's not going to come up. And this one is literally after 0.6. It's literally 1. So this one's not the correct answer. Therefore, confirming that the number 1 is the correct answer. If we look at it through a mathematical analogy, 0.6 divided by 0.1 is 6, which is a whole number. Now 0.6 divided by 0.5 gives us a decimal, and 1 divided by 0.6 also gives us a decimal. Only this one gives a whole number, so this is the correct answer. This is the next question we're looking at, question number 2, but it's a two-part question, but essentially one. Anyways, this is also from the specimen paper and 4.1.1.4 from the specification. So again, I suggest giving it a pause and having a go before I go through it. S power equals energy transferred over time, which you will be given in your formula sheet. So it's pretty straightforward. Now, looking at the second part of the question, this was the information that we were given, and we are meant to find the mean power supplied by the sun to the water in the pan. Now, the formula of power is energy transferred over time, and we can see the energy transferred right here on the first line is 1050 joules. The second value we need is time, which is given here, which is 5 minutes. However, the SI unit of time is seconds and not minutes. Now, what is SI units? SI is the metric system that is used universally as a standard for measurement. So basically, since time has so many different units, it has hours, minutes, seconds, milliseconds, we need a standard one which everyone can use, which makes it much easier to compare values because then everyone has the same number as the answer. So that one for time is in seconds, and in GCSE physics you're meant to use the SI unit for everything. So we have to convert these minutes into seconds, which we would times by 60, which would give us 300. And we have the energy transferred, we have the time, which we converted into seconds, which is 300. So since it's energy transferred divided by time, we're going to divide 1050 over 300, which gives us 3.5, watts. Now I recommend learning the SI units for every single one, for energy, for everything, and I'm gonna attach a document in the description below for the SI unit of every quantity you need for GCSE physics. So please check that out. See what the examiner is exactly looking for when they're marking your work. So they do accept the final answer with no working shown, but however, for each stage of the work you can get a mark. So even if you make a mistake, you can get marks. So obviously show the working. So we're meant to find the mass of the water, and we are given the specific heat capacity in the question. They wouldn't give it to us if it wasn't relevant in some way. So let's look at the equation of specific heat capacity, which is on the equation sheet. So we've got the change in thermal energy. Now the energy transferred to the water is 1050, so that is the change in energy because that much energy was transferred. And then the mass, which we have to find, times it by the specific heat capacity given to us in the question, and the temperature change, which is zero point 0.6 because the time taken for the water temperature to increase by zero point 0.6, so that's the temperature change. And then we multiplied we multiplied 4200 into zero point 0.6, which gave us 2520. Then we rearrange this equation and by dividing 2520, and then once we divide this, we get this answer. Now since the third digit is where the 6 starts going recurring, we round it down to 3 significant figures, which gives us this. Scheme, just to give you an idea again, so what this question is asking us is that the student's result can only be used as an estimate of the mean power at her location, and we have to give one reason why. So the student's value of the time it took for the temperature of the water to increase is not the exact value, it's a bit off from the exact value, and we need to answer why. So there can be multiple reasons for this. This is a snippet from the mark scheme. As you can see, there can actually be 4 possible answers to this question. So let's go through each one of them and see why they are the correct answer. The first one says that energy is used to heat the metal pan as well as water. So the aim of this experiment is to find the time it takes for the temperature of just the water to increase. But in her experiment, there's a pan, so obviously, before the temperature of the pan of the water could increase, the temperature of the pan is also going into consideration in her experiment. So two things are being heated and not just one. So it could possibly take longer. So her estimate could be more than the exact value, and that's what makes it an estimate in the first place. Now, some of the energy is transferred to the surroundings, so it's possible that first the energy goes to the pan and then it just radiates into the surroundings, so the energy is wasted. Um, the third possibility is that the angle of solar radiation will have changed during investigation. So when she was experimenting, that time the angle of solar radiation was different than normal. And when the angle of solar radiation changes, the amount of energy also changes. Um, so yeah, and then the intensity of solar radiation may have varied. So when she was carrying out the experiment, the intensity was more or less than usual, which changed her estimates. Which changed her answer, which is what made it an estimate. They just asked for the equation which links gravitational field strength, gravitational potential energy, height, and mass, and so the answer is pretty straightforward. It is GPE equals mgh, and I'll show you one in the mark scheme as well. So this is the version of the mark scheme. This is the next question I want you to have a go. We have to calculate the change in gravitational potential energy from the position where the student jumps to the point 20 meters below. So try to remember the formula for the change in gravitational potential energy, which is the mass multiplied by the gravitational field strength, which over here is given, and the mass is also given, multiplied by the height. And it says the height in the question where the student jumps to the point 20 meters below, as you can see. and you just plug that in into the equation and you get this answer. So 80% of this change in gravitational potential energy store. Now remember, we calculated this in our previous question. So the answer to the previous question is the gravitational potential energy store. And that has been transferred to the kinetic energy store. How much has the student's kinetic energy store increased after falling 20 meters? So we just need to find 80% of the gravitational potential energy, which from our previous answer was 9,800. Now to find 80% of it, first we're going to divide 80 by 100. Okay, remember, whenever you're finding percentages, you always divide the number by 100 first. So if you're finding 80%, you're going to divide 80 by 100. This gives you this value, which is the multiplier. And since you're finding 80% of 9,800, you multiply the multiplier by 9,800, which gives you 7,840. Speed of the student after falling 20 meters. Now think about the formulas that have speed, and it relates to the information you have. Now, a common formula of speed is distance over time, but we actually don't have the distance all the time. And another formula that speed would be used in is the kinetic energy formula, which is half mv square. And if you think about it, we actually have all of this information. So v is the speed which we have to find, mass is given right here, 50 kg, and kinetic energy, if you remember, we calculated in our previous question. So we just plug all of that into the equation, and here is a snippet from the mark scheme so you can see exactly how it's laid out and what the examiner wants. So as you can see, we plugged in the answer from our previous question, half, into the mass we have, 50, and into v square. Now you rearrange this. So since half and 50 are multiplying, you divide them because you do opposite of what's being done in the equation. So you're dividing them by 7,840, and then since it's squaring, you're going to square root the other side, and that leaves us with this, and we have to give the answer to two significant figures, therefore it's going to be 18. This is the final question, and in this question we're meant to find the spring constant of the bungee cord. Now our formula we know for a spring constant is elastic potential energy equals 0.5 times spring constant times extension. So we're going to use this one. Now, the definition of elastic potential energy is the energy stored in a stretched spring, and a bungee cord is essentially a type of spring. So in our question it says the energy stored in the bungee cord is 24.5, so that's the elastic potential energy. However, 24.5 is in kilojoules and the SI unit of energy is in joules, so we'll have to convert that into joules by multiplying it by 1,000. Let us now look at the mark scheme. In the mark scheme, the extension is 35 meters. Now, how did we get that? So essentially, extension is the additional length of a spring when a force is applied. So on the right hand side, we can see first the length of the bungee cord is 20 meters, but then after the force is applied, after the person jumps, it gets stretched, a force is applied, so the length becomes 55 meters. Now what is the extra length that was added? For that, we just do 55 minus 20, which gives us 35. So now we plug in our extension and our elastic potential energy into the original equation, and then to rearrange the formula to find the value of K, we divide 24,500 by half and then divide it again by 35 square, and if you do that in your calculator, that will give you the answer of 40, which is the spring constant. Thanks for watching. I hope you found this helpful.